Okay, so what we've just looked at is essentially the elements of probability theory. So we've talked about experiments, outcomes and events, and we've looked at the probability function. And we then defined the concepts of marginal, joint and conditional probability. And we're now going to look at random variables and the probability distributions associated with those variables. Now, the rules of probability are relevant here, so we're building on them because the rules of probability allow us to define the concept of a random variable as a function from the sample space that maps to a set of real numbers. And random variables are important. The reason they're important is that the data that we observe and analyse in the real world, we can conceptualise data as the observed or realised values of random variables. So what we're going to do in this section is we're first going to introduce random variables theoretically, so I'm going to characterise them, and then we're going to link them back to probability explicitly by looking at probability distributions. And let's start with the definition number 9 of a random variable. So a random variable is very simple. It's a function defined on the sample space that associates a real number with each possible outcome in the sample space. Okay, so it's going to associate each small omega with a real number. Formally, we're going to regard x, the random variable, as a possibly many-to-one mapping from omega to r. Random variable, okay, so it's mapping from the sample space to the real line, mapping each element small omega to a value small x. And the implication is straightforward and obvious. It means that we can associate any sample space for any experiment or process with a sample space that is an actual set of real numbers rather than some other concept such as heads or tails or whatever. It's a set of real number in which the events are subsets. So omega, small omega, element of the sample space, is an event or a possible outcome. X is a real number, and that real number could be binary, it could be integer, or it could be continuous, and the random variable is mapping each of these outcomes and events to a real number. Now, an important point here concerns notation. We're going to use the convention in statistics that capital X represents the random variable itself and small x represents a particular or realised value of that random variable. So that's one. Might think of it as one realised value. This is the random variable which can take many of these different values. Okay, that's the standard notation. So, the first important distinction to introduce in random variables, and it really is key because it determines how random variables and their associated probabilities are represented, is the distinction between discrete and continuous random variables. So first, a discrete random variable. A random variable is discrete if the set of all possible values that the random variable can take, denoted by this symbol here, is countable. So it's got a countable number of discrete values shown here, x1 up to xn, or it could be infinite actually. That is a finite or infinite set of distinct values that the random variable can take, and typically these are often integer values. So in terms of interpretation, discrete random variables are used to describe outcomes of experiments that involve counting or classification. And we talked about that earlier. We talked about experiments that involve counting as being discrete. A continuous random variable is one that has a set of values that take this form here. So essentially, a continuous random variable can take any value on the real line, and here we've written it as, for any two real numbers, ai and bi, the continuous random variable is the union of intervals in R. Crucially, unlike discrete random variables, it's uncountable. So the range of x is uncountable. And in terms of interpretation, continuous random variables are used to describe the outcomes of experiments that involve measurement. And again, we talked about that in the previous part of the lecture. Okay, so let's give some examples here. Random variables, events and outcomes. This is just bringing it all together. Here we have an experiment. It's coin toss, and the two outcomes are heads or tails, we want to define a random variable x, and what we're going to do is map it to numbers, and that's what a random variable does. So we're going to map it to the numbers 0 and 1. In other words, this is a binary random variable. It can take two numeric values, 0 or 1. Another experiment in the broadest sense: how many days might it rain in the month of May? This again is an integer random variable with values ranging from 0 up to 31. So 31 distinct values are the sample space that this can take, and that is mapping x to a real number. Another example, same kind of thing, number of goals in a football match. Well, it could be 0, it could be 1, it could be 2, 3, blah, 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 so on. Again, mapping this experiment to a set of real numbers. Or it could be an experiment in terms of temperature. How hot is it going to be tomorrow? Well, that's some number, a continuous number greater than some minimum value, say. So that should be hopefully make it really clear. A random variable is a way of describing outcomes in terms of real numbers. In the examples we're looking at here, A is a discrete random variable. It's binary, it can take the values 0 or 1. B and C are also discrete random variables. They're in this case non-negative integers. And D is a continuous random variable. It takes values on the real line. Now that's random variables, hopefully very simple and clear. I now want to talk about the probability associated with random variables. And the probability of random variables taking a given value or a given range of values is expressed and calculated using what's known as probability distributions. And there are different types of probability distributions depending on the process or experiment under consideration. So for instance, the probability distribution for a coin toss will be different from the probability distribution that we would look at, for instance, in looking at travel times to get to college. They're two different experiments, two different processes, and they involve different probability distributions. What I want to do first of all is just define what's meant by probability distributions, characterize them for discrete and continuous outcomes, and then we'll look at some examples. So a probability distribution is a function denoted in this way here, a function with respect to random variable x taking input values small x that assigns probabilities to the possible value of a random variable. That's what it's all about. It thus allows us to calculate in the discrete case what's the probability of random variable taking some specific value, or in the continuous case what's the probability of random variable taking some value less than or equal to a specified value of x. So it allows us to calculate these probabilities for each x in a suitable range of the values that x can take. Now just to be clear, we define this symbol here, we call this the support of the probability distribution. And essentially, the support of the probability distribution is a set of values or points for which the probability distribution is not zero valued. So the probability distribution of the random variable is positive on the set defined by the support. That's all it means, and you can look at this in your own time. That's all this says. X is referred to as the support of the distribution. It's the set of x for which the probability distribution takes a positive value. Now the probability distribution is really just a real valued function of a single real argument. It's as simple as that. But of course it has to satisfy the rules of probability, and so those axioms of probability, as they applied to probability calculations in general, are going to apply also in the case of probability distributions. And as I said, an important distinction is between discrete and continuous variables, and that's because there's two distinct ways of specifying probability distributions. In the case of discrete random variables, we refer to the probability mass function. That is the probability distribution for a discrete random variable. For a continuous random variable, we talk about probability density functions. Okay, and we're going to look at both of those now. Okay, so in the discrete case, we have the probability mass function. This is the function defined on the support of the distribution that tells us the probability of x taking some specific value in an appropriate range of x. So it's assigning probabilities to each value that the random variable x can take. This is in the discrete case. As I said, the rules of probability must apply, and the function fx is a probability mass function if and only if the probability that it generates are non-negative, and the sum of those probabilities must come to 1. So this is simply applying axiom 1 of probability, and this is simply applying axiom 2 and 3 of probability to be consistent. Okay, so the probability of the entire sample space must equal 1, and there must be a sum over disjoint sets within the distribution. So that's what this is saying. That's the probability mass function. It's a discrete case. We can also define a cumulative distribution function, and it's defined by this equation here. We denote it, the probability mass function denoted by small f, and the distribution, cumulative distribution function denoted by large X. And as you can see, it's a summation over the probability mass function. And what the cumulative distribution function is telling us is it's telling us the probability that random variable x takes a value less than or equal to xi. Oh, sorry, less than or equal to x. Okay, that's what it's telling us. That's why it's called cumulative, because it's summing. And thus, in the case of the first element of the range of x, the probability mass function and the cumulative distribution function are the same, and we can calculate the probability of any particular value of x by taking the difference of successive values of the cumulative distribution function. So we can use either the probability mass function or the cumulative distribution function to describe the probability distribution of a random variable x. Now, the cumulative distribution function is useful because it can be defined for not only discrete random variables, but also continuous. And actually, for continuous random variables, we're going to start with the CDF. So this is the continuous case. Same principle. The cumulative distribution function, large F x for random variable x, is defined on the real line by this expression here. So the cumulative distribution function is telling us the probability that random variable x takes a value less than or equal to small x, so some specific value that we can choose. That's the cumulative distribution function. As I said, probability distributions are represented differently for discrete and continuous random variables. For a continuous random variable, the probability distribution is called a probability density function. And we define it first of all with respect to the CDF, and it's defined in this way. So in this equation here, this is the CDF on this side, and this expression here is the probability density function. So the PDF is simply the sum or the integral over all values that x can take up to some specific defined value x that the CDF, that is the argument of the CDF. So that defines what the probability density function is using calculus. It's this integral, the cumulative distribution function is the integral of the PDF. And we can use that definition to then say, okay, for any interval AB, probabilities can be computed for a continuous random variable using this expression. So the probability that the random variable x takes a value that value a, that a is less than or equal to random variable x less than or equal to b, so within this range, is equal to the difference of the CDF at those two particular values, which by the rules of calculus is equal to the integral between a and b of the probability density function. So that's how it works, and all we've used is the this is basic calculus in order to get from this expression here to this expression here, which defines the probabilities in terms of the probability density function. Now again, the rules of probability must apply to the PDF. So the function is a PDF if and only if the probabilities that it generates are non-negative, and the integral must, the function must integrate to 1 over all values that random variable x can potentially take. Now, I hope it's obvious why we need to talk about probabilities in terms of ranges rather than individual values for the continuous random variable, but just to be absolutely clear, in the case of discrete random variables, the probability mass function or the cumulative distribution function define probabilities for each distinct value of x, and that's because the support is countable. In the case of continuous random variables, the probability density function or the cumulative distribution function define probabilities over ranges of x. And this is because the set of real numbers forms a continuum with infinitely many values. The support is not countable in this case, and therefore the probability of x taking any one specific value must be infinitesimally small or zero, and that's what this expression here says formally. But I hope that that's obvious anyway. Okay, so in the next part of this section, we're going to look at specific probability distributions, specific PMFs and PDFs. And I just want to make one final distinction before we go on to do that. We're using probability distributions to model populations, and what we can distinguish is a family of distributions from a single or observed distribution. So a family of distributions is indexed by one or more parameters that determine some characteristic of its distribution, such as its shape. And a family of distributions is appropriate to a specific type of process or experiment, a coin toss, waiting times, that kind of thing. So for example, a distribution we'll talk about quite a lot, and it's one of the most well known, is the normal or Gaussian parametric family. And this parametric family is defined by two parameters, mu and sigma squared, mu being the mean or expectation and sigma squared being the variance. So this is the equation for the normal distribution that we use to calculate probabilities. So the parametric family of the distribution describes the overall functional form, such as shown here, while the characteristics of a particular distribution are determined by the specific values that those parameters take. So for instance, mu could be 0 and sigma squared could be 1. That gives us a specific type of normal distribution. So what I want to do now is just review some common families of probability distributions that are used to represent discrete. We'll deal with discrete random variables first, and then continuous random variables.